See, once again, the steps for analog filter design. First, find the order of the filter from the given analog specifications. Find the order of the filter. Then find the cutoff frequency for the Butterworth filter. Depending on passband or stopband requirement, I suggest do using the passband requirements. It will be simple, not much of, again, taking the average, all that is not required. So based on the passband requirements, calculate the cutoff frequency. That is your second step in the design procedure. Then once you know the order of the filter, you can calculate the poles of the transfer function. Calculate the poles of the transfer function. How many n poles you're going to get? N poles of the transfer function. Then once you have done that, write down the normalized transfer function Hn of s as 1 by Bn of s. Bn of s is the Butterworth polynomial. How do you obtain that? Product of all the left half poles. That is the ones that you have calculated, s minus sk. Multiplying all the poles, you get the Butterworth polynomial. Write down the normalized transfer function. Okay, the final step will be HA of s to find the analog transfer function. In your normalized transfer function Hn of s, replace s by the corresponding transformation, s by omega c for a low pass filter. So this function here is like a prototype. This is what is the prototype that we design in a Butterworth, in an IIR filter in general. The normalized transfer function that acts like a prototype for the IIR filter design. Okay. Next, for the digital filter design, we are interested in designing digital filters only. Okay, but this is the procedure that we follow for an IIR filter. First, you should understand how to design the analog, and then we are going to concentrate on the designing the digital filter. So when you are designing a digital filter, there are going to be steps that is added in the beginning and in the end. Okay, why in the beginning? Because the analog specifications are given to you and you designed this filter now, isn't it? Whatever the data that was given to you was the analog specifications. How do you know it's analog specifications? Look at the frequency component that is given to you. The units were in radians per second, isn't it? That is the analog angular frequency. So when the analog filter specifications are given to you, this is what the procedure that you have to follow. Steps 1 to 5 that we have listed here. Okay. But when you go to the digital filter design, when you have to design a digital filter, the digital specifications will be given to you. That is, this omega in radians is what will be given to you. Okay. But what is the prototype that we know that we have to design? Is this procedure to be followed. Okay, so anywhere in this procedure, we are not using the digital frequency omega. We are using the analog frequency omega to design this analog filter. So what you have to do in the beginning is convert this digital specifications into analog specifications. I am talking about the spec. Okay, I'm talking about the specifications, not the method. Method is it different, depends on the different kinds of techniques that we have to design the digital filter. I'm just talking about the specifications as of now. So the digital filter specifications will be given to you. That needs to be converted to the analog filter specifications first. Then all these steps have to be followed to design the analog filter, and then you have to apply the analog to digital transformation. Analog to digital transformation to obtain the digital filter. So now what we have to learn is how is this analog to digital transformation done, or what are all the different kinds of transformations that we have to convert an analog filter to a digital filter. Okay, I've told this previously also. Once again, I will repeat here. There are 4 kinds of digital transformations, the analog to digital transformations available to us. It is called as the backward difference method. One is the backward difference method. Next is the matched Z transform. Then you have the impulse invariant transformation. And then we have the bilinear transformation. These are the 4 kinds of analog to digital transformations available to us to convert this analog filter that we have designed into the digital filter. Okay, this is one way of designing an IIR filter. First design the analog, then convert it to digital. When I say we are converting analog to digital, that means what? You have designed H of S now. This needs to be converted to H of Z. Okay, the transfer function of the analog filter should be converted to the transfer function of the digital filter. H of Z needs to be found out. Okay, that is the transfer function of the digital filter. So this relationship between S and Z needs to be found out. What is it that you're going to substitute for S so that you get Z? So the relationship between S and Z becomes important. So in each of these methods that I have told you here, there are different ways to convert S to Z. Different ways to convert S to Z. Each of them has its own advantages and disadvantages. Okay. Among that, bilinear transformation is found to be the best transformation for analog to digital. Okay, because some of these transformations also bring about the possibility of aliasing. That also happens. What is aliasing? Overlapping of frequencies. Okay, so that happens because you are mapping the values from one domain to the other domain. From the S domain, you're mapping it to the Z domain. So all the poles that you have in the S domain should be transformed to poles in the Z domain. How you're going to do that? How you're going to transform these poles, right? Is the question here for analog to digital conversion. So whenever you're mapping the poles from the S plane to the Z plane, the mapping should be proper. Okay, it should not get overlapped. The poles should not get overlapped, the frequencies that we are talking about. So that problem sometimes is there in the other kinds of transformations, which is not there in the bilinear transformation. Okay, so bilinear transformation happens to be one of the best transformations to convert the analog filter to the digital filter counterpart. Okay, is that procedure clear to you? So far what we have seen is only the analog IIR filter design. Now we'll have to learn this bilinear transformation to convert the analog filter to the digital filter. So once you learn this transformation, you will also know what when a problem is given to you, what are the specifications that you have to take? Okay, design that filter and then convert it to digital. It's a little roundabout, we can say. That's how it is. So first, let's take up the bilinear transformation. Try to understand how that S to Z relationship is. Basically, as I told you, we are interested in relating S and Z. Once you get this relationship in your H of S, just replace S with whatever the relation that you have derived. You are going to obtain your H of Z. H of Z. So that's how the transformation goes on. So let us see how to perform this bilinear transformation and derive the relationship between S and Z. So that is like the overall picture of the digital filter design. Bilinear transformation. In short, it is always called as BLT. BLT, bilinear transformation. So bilinear transformation, we'll have to see the mapping from the S plane to the Z plane. When I say mapping, it's just what the relationship that we are deriving between S and Z. That's all, because we want to convert H of S to H of Z. Okay. So now what we will do here is we will consider a simple transfer function H of S, which is of the form B by S plus A. B by S plus A. So this is a very simple transfer function which has only one pole in it, isn't it? At S equals minus A. You just have only one pole at S equals minus A. So it's a first order filter. It's a first order filter. For this filter, we will derive the relationship between S and Z. So once you know what is the substitution you have to do for a first order, the same thing holds good for second order. Okay, we don't have to again worry about a second order filter or a third order filter, what should be the substitution and so on. We are just taking a simple one pole filter and we'll try to find the relationship between S and Z. The same thing can be applied to the higher order filters as well. Okay. Yeah. So this is your H of S. You know H of S is output Y of S by input X of S is equal to B by S plus A. Right? Let's cross multiply. So you get S into Y of S plus A into Y of S equals B into X of S. Now let's write the inverse Laplace transform. S into Y of S, inverse is dy of t by dt plus A, Y of S, inverse is Y of t. They are going to be continuous signals, isn't it? Laplace is always for continuous signals. Z transform is for discrete signals. B into X of t. B into X of t. By writing the inverse. Writing the inverse. Okay. Now what we are going to do is we are going to integrate this equation between the limits n minus 1 into t to nt. We are going to integrate the above equation between the limits n minus 1 into t to nt. So let me write that. Integral n minus 1 into t to nt dy of t by dt, integrate with respect to t. So plus a constant outside, integral y of t dt equals b n minus 1 into t to nt x of t dt. We are integrating the entire equation with respect to t between the limits n minus 1 into t to nt. Okay. Now how do you find the integral of this? The first integral is anyway y of t between the limits n minus 1 into t to nt. But how about these two terms? These terms, how do we integrate? For this, we make use of the trapezoidal rule. So what is this trapezoidal rule and what is it given as is when you're integrating a value between two limits, any two limits. So if you're integrating a signal y of t between these two limits, it can be written with the trapezoidal rule as y of nt, that is the upper limit, plus y of the lower limit n minus 1 into t divided by 2 the whole thing into t, or multiplied by the constant t by 2. So this is called as a trapezoidal rule of integration. So we are going to make use of this rule in the above equation. So same thing can be applied to x of t also. So the first integral is anyway y of t, isn't it? Because dy of t by dt into dt, that will become y of t between the limits n minus 1 into t to nt plus constant a we have. Then for integral y of t, if I use the trapezoidal rule, so it's t by 2 into y of nt plus y of n minus 1 into t equals, right hand side we have constant b and t by 2 into x of nt plus x of n minus 1 into t. So
Excuse
the
me, ma'am.
first one, yes.
Why have we taken only those two limits, ma'am?
Which one?
N
No.
minus 1 into T to T.
Yeah, that is because the present value and the past value, it is something like that. See here, basically, we are trying to convert the continuous time to discrete. Okay, even in the backward difference method or in the other methods also, some conversion between continuous time to discrete time is what we are looking for. So these two limits, what it will do is it will give me the present value and the previous value, isn't it? N is my present value, n minus 1 is the previous value. Just the two values, the present and the past values. We are taking the integral between the two. And now you can see that the differential equation which we had here, the differential equation, okay, that is dy of t by dt plus ay of t equals bx of t, what we have, that we are trying to convert it to a difference equation. Why difference equation? Because we are talking about converting the analog to digital filter. We're talking about a transformation of the analog to digital. So these are ways and means of converting a continuous time system to a discrete time system. Okay, so even in the backward difference method, what we do is we take the difference between the present and the past samples. That is the reason why we do that. Just a delay of a difference which we are seeing between the values. Okay. They are just ways of converting the analog to digital. That's all. Okay. Yeah. So now let's substitute these limits. So y of nt minus y of n minus 1 into t. Plus at by 2 y of nt plus at by 2 y of n minus 1 into t. Okay, right hand side bt by 2 x of nt plus bt by 2 x of n minus 1 into t. Yeah, now this t is nothing but the sampling period. T is nothing but the sampling period. That's how you convert the analog signal to a digital signal, isn't it? With the process of sampling. With the process of sampling, you're converting the analog signal to digital signal. So something similar we are doing here. We are trying to write the system, the analog system that we have in terms of a difference equation. Okay, now since it's a first order system, we are writing the first difference, you can say. The first difference, nt and n minus 1 into t. So as we go with the higher order, second order, third order, it will become a little complex. So we don't want to do so much of complexity. For a first order system, if we can derive, the same thing can be applied for second order and third order. They are just ways and means of converting an analog system to a digital system. Okay, like that we have different methods. For example, in the approximation of derivative, which is the backward difference method, for every difference, okay, for the first derivative we take the first difference, for the second derivative we take the second difference, and so on. In that way we derive the difference equation in case of a backward difference method. For each method it is different. For each method it is different. For bilinear transformation, this is how we do. We integrate that. And see what happens once you integrate a continuous time signal between two limits. You are reducing the values to just the two values, isn't it? The continuous range that we had, we are reducing it to two values, the present and the past sample, because it is a first order system. It's a first order system. Same thing can be extended to the higher order systems as well. Okay, instead of deriving for that, we just extend this concept to the higher order systems. I hope that's clear. Okay, now we can simplify this equation and write. So simplify in the sense, instead of writing that t every time, capital T is a constant, where only in this signal I'm talking about. You have y of nt, y of n minus 1 into t, right? So all these places, they are discrete time signals now. So for a discrete time signal, do we keep writing every time x of nt, y of nt? No, right? We just write it as x of n, y of n, like that. Why? Because that t is understood there. It is sampled at those instances. So it's understood that you have a capital T there. So instead of writing the signal as y of nt, y of n minus 1 into t, we will write it in the form that we are used to writing always, that a discrete time signal. Okay, let me write it in the next step only. Nt. So instead of writing it like that, we will write it as y of n minus y of n minus 1 plus at by 2 is a constant. So here you cannot remove t. Y of n for the signals I'm talking about. At by 2 y of n minus 1 equals bt by 2 x of n plus bt by 2 x of n minus 1. X of n minus 1. So you see, we started off with an analog signal, isn't it? Analog system, h of s, right? We wrote the differential equation in terms of dy of t by dt. Now what have we got? We have derived a difference equation from the differential equation. So this is one way of converting an analog system to digital system. Integrate the signal, the system equation between two limits. Okay. See, some cases also you can also take n and n plus 1. You could ask me, you can take n and n plus 1. Why don't we do that? You can take n plus 1, but what happens when you take n plus 1? You end up with a non-causal system, isn't it? N plus 1 depends on the future value. We are not interested in designing non-causal systems as of now. Okay, the traditional or most of the conventional systems that we deal with are linear, time invariant, causal and stable. That is what we are interested in designing the systems. You can talk about applications where you want to design a non-causal system, or you want to, of course, no one wants to design an unstable system, right? Yeah, so that since that is the motive, we take the sample nt and n minus 1 into t, the past sample, so that we derive a causal system. Okay, the mapping also, when we are transforming the system, it should be done properly. That is why we take only the left half poles, so that you end up with a stable system and not an unstable system. Okay, so all these will be taken care of whenever you are designing a system. So that's the reason we take the present and the past sample, so that we get a causal system. Okay, so what have we got now? We have obtained the difference equation from the first order analog transfer function. Okay. So once you have got the difference equation, now we'll have to rearrange all these terms and write it in terms of h of z. Okay, write in terms of h of z, so that you compare h of s and h of z and get the relationship between s and z. Get the relationship between s. So now let us group the y of n terms to one side. So 1 plus at by 2 into y of n. Then let's take minus common for y of n minus 1 term. 1 minus at by 2 into y of n minus 1. On the right hand side, bt by 2 into x of n plus bt by 2 into x of n minus 1. Now let's take the Z transform on both sides of the equation. So 1 plus at by 2 is a constant into y of z minus 1 minus at by 2 z bar minus 1 y of z equals bt by 2 x of z plus bt by 2 z bar minus 1 x of z. So let's take y of z common on the left hand side and x of z common on the right hand side, and then write down y of z by x of z. So y of z by x of z will be bt by 2 is common, 1 plus z power minus 1 in the numerator, divided by 1 plus at by 2 minus of 1 minus at by 2 into z bar minus 1. So now we have to simplify this in such a way that we can compare this with h of s, which we had assumed as b by s plus a, right? So what is y of z by x of z? It's nothing but h of z, the transfer function of the digital filter. So let's multiply and divide by the term 2 by t into 1 plus z power minus 1. So we have bt by 2 into 1 plus z power minus 1 here. In the denominator also 2 by t 1 plus z power minus 1. So this term will multiply and divide with the numerator and the denominator. So 1 plus at by 2 minus of 1 minus at by 2 into z bar minus 1. So in the numerator, this term gets cancelled out. 2 and t also gets cancelled out. So you are left with b in the numerator, right? Then in the denominator, let us rearrange these terms in the square bracket that we have. So how we are going to rearrange that is 1 minus z power minus 1, okay, plus at by 2 we can take it common, 1 plus z bar minus 1. So why we write like this is we can cancel out the terms with the factor that is outside the bracket. So now if we simplify the denominator, so you have b divided by 2 by t into 1 minus z inverse by 1 plus z inverse plus 2 t gets cancelled, 1 plus z inverse also gets cancelled. You are left with just a here in the denominator. So what is this? The digital transfer function h of z. So we started off with the analog transfer function h of s equals b by s plus a, and derived the digital transfer function h of z. So now we can relate h of s and h of z, right? So what will be the relationship if you compare? That is b by s plus a, and here you have b by this term with z inverse plus a. So obviously what is s equal to? 2 by t 1 minus z inverse by 1 plus z inverse. So in the analog transfer function h of s, if you replace s with this term, then we are going to get the digital transfer function h of z. So this is called as bilinear transformation. So this transformation that we have obtained is called as bilinear transformation. Now in order to see the mapping of the bilinear transformation from the s plane to the z plane, we'll have to substitute for s and z. As, so you put z is equal to r e to the power j omega and s equals sigma plus j omega, and we substitute this in the above equation. What do we get? S is sigma plus j omega and 2 by t 1 minus, okay, we can write this bilinear transformation as 2 by t. If you have to write in terms of z, it becomes z minus 1 by z plus 1. So that becomes little easier for us to simplify. So that can be written as r e to the power j omega minus 1 by r e to the power j omega plus 1. So the polar form which we have r e power j omega can be written in the rectangular form, and we need to compare the left hand side and right hand side. Therefore you have to separate out the real part and the imaginary part on the right hand side equation. So how can we do that? 2 by t, write this as r cos omega plus j r sin omega minus 1 divided by r cos omega plus j r sin omega plus 1. Now you will have to rationalize this. So group the real terms to one side and the imaginary terms to the other side and rationalize it so that you can separate the real and imaginary parts. So r cos omega minus 1 is the real part plus j r sin omega is the imaginary part. R cos omega plus 1 plus j r sin omega. So how do you rationalize this? Multiply and divide by r cos omega plus 1 minus j r sin omega divided by r cos omega plus 1 minus j r sin omega. So we need to multiply the denominators and the numerator and simplify this term, separate out the real and the imaginary part of it and compare with the left hand side. So the real part will be obtained as sigma, you're going to get 2 by t into r square minus 1 divided by 1 plus r square plus 2r cos omega, and omega equals the imaginary part. If you compare, you're going to get this term 1 plus r square plus 2r cos omega. So that will be the imaginary term. Now here we can clearly see that if you look at the real part of this, that is the sigma value which we have, equation 1, call this as equation 1 and equation 2. So if you look at equation 1, if the value of r is less than 1, right, obviously sigma will be less than 0 or a negative quantity. Therefore, what does that mean? The left half of the S-plane gets mapped to inside the unit circle in the Z-plane, resulting in stable poles, right? Similarly, if r is greater than 1, then sigma is greater than 0. So the right half of the S-plane maps to outside the unit circle. So anyway, we are interested in the left half poles, which results in a stable system, which is getting mapped into the unit circle. So in the Z-plane, if the poles are inside the unit circle, then the system is stable. So the stability of the system is maintained and that does not change. Then the third case, where if you put r is equal to 1, then obviously sigma becomes 0, but we can write the relationship for frequency omega as 2 by t into 2 sin omega by 2 plus 2 cos omega. And if you simplify this on the right hand side by writing sin omega as 2 sin omega by 2 cos omega by 2 and 1 plus cos omega as 2 cos square omega by 2, we can get the right hand side as 2 by t tan omega by 2. Tan omega by 2. So this relationship between the analog and digital frequency in the bilinear transformation, as you can see here, right, omega can be written as 2 tan inverse of omega t by 2. So if we plot this two frequencies, the analog versus the digital frequencies, right, It is actually a non-linear relationship because we have the tangent function in it. Okay, so the lower frequencies in the analog domain are getting expanded in the digital domain, and the higher frequencies are getting compressed in the digital domain. Okay, so that because the relationship is non-linear, this kind of behavior is called as frequency warping. This kind of behavior is called as frequency warping, which is introduced by bilinear transformation. So what do we do in order to overcome this frequency warping is, whenever the digital frequency specifications are given to you in the problem, using this relationship of ohm equals 2 by t tan omega by 2, we find the analog frequencies, then design the analog filter, and then apply bilinear transformation. So what is happening is, we are using this relationship of the analog and digital frequency 2 times. Right, so this step of converting the digital frequencies into analog is called as the pre-warping step. So we pre-warp the frequencies before we design the analog and the digital filter, and then when you apply bilinear transformation to obtain the digital filter, right, the effect gets nullified. The warping effect gets nullified and the frequencies will be placed properly. Okay, so this is bilinear transformation to convert an analog filter into the digital filter.